Hello everyone, welcome to yet another EOL seminar. I'm pleased to introduce Dr. Adam Fleisher as our speaker today. Adam is a research chemist at the National Institute of Standards and Technology in Gaithersburg. Before that, he was a National Research Council postdoctoral fellow at GILA right here in town, so he's somewhat familiar with Boulder. He holds a PhD in physical chemistry from the University of Pittsburgh, along with a BS in chemistry from Elizabethtown College. He's active in the Optical Society of America. He's also a member of the American Chemical Society, the American Physical Society, and the American Association for the Advancement of Science. His research involves the development of advanced optical sensing techniques and precision molecular spectroscopy techniques using optical frequency cones, quantum cascade lasers, and -S optical resonators. Today he's going to tell us about development of a cavity ring-down spectroscopic technique for high-accuracy absolute measurements of carbon isotopologues of CO2, and some things that, if you're paying attention, should make you say, wow. Adam?
All right, thanks a lot, Mike. All right, it's a pleasure to be here, and I really appreciate the invitation to come and share with you some of our laboratory research going on in Gaithersburg. So, yes, I still get sort of sideways looks when I tell people that I made the switch from NIST Boulder to NIST Gaithersburg. It's not the direction most people think they'd like to move, but it's been a lot of fun to join the lab in Gaithersburg. So I'll share with you a little bit. Again, this is laboratory work focused on accurate spectroscopy, not just high precision, but accurate spectroscopy of CO2, and the general motivation involves populating reference databases which are useful for modeling radiative transfer and things along those lines. And we'll also touch a little bit on our efforts in focusing on isotopes, C13 and C14, building optical measurements for making optical instruments for making accurate measurements of those species. So the real broad motivation, so this is a very NIST slide. So does everybody have this on their calendar for the 16th? It'll be real early in the morning, right? So this has been talked about a whole lot at NIST, but beginning on the 16th, the working committee in France, in this case, will hopefully, surely, vote to redefine the world's measurement system. So there will no longer be any physical artifacts that underpin the international system of units. So the last shoe to drop is the kilogram. So the kilogram in that case will be replaced and linked to a fundamental constant. So the idea is to find true invariants of nature to which you can link measurements of mass or the second or the kilogram. And remove the need for physical artifacts in this system. So the hope is that the new SI, among other things, will also improve scalability when it comes to making precision measurements or making accurate measurements as well. So the accuracy diminishes when you try to make a measurement further away from your reference material. So the further away from a kilogram you are, the more difficult it is to be accurate. That sort of scalability problem is hopefully removed by this redefinition. So the question we've been asking ourselves in our lab is, can we extend these sort of principles of defining a measurement system based on a true invariant of nature? Can we extend that to something like stable isotope analysis, or even measurement of radiocarbon amounts in a sample of carbon? So pictured on the left is an example of the radiocarbon standards that traditionally NIST has managed and distributed. So there's an oxalic acid 1 sample, which is almost entirely depleted. There's about a pound of it remaining. And then you have sort of the secondary standards. So in these systems, you have a tendency to get, the possibility for creeping of scales. If you generate one reference material, then you have to link it to the next one, and link it to the next one, and so on and so forth. So from our perspective, that's an opportunity for the accuracy to diminish in these sort of measurement scales. So the specific experiments I'll address today from within the gas sensing metrology group is we'll talk about making a tabletop optical instrument for measuring radiocarbon at ambient levels, so fraction modern 1 or below. And then I'll introduce some absolute isotope amount ratio measurements. This is unpublished work that we're just starting to get written up and get together. But the idea here is to not measure C13, C12 ratios on a delta scale, but make an absolute measure of the ratio in the material. So we'll talk about that. If I have time at the end, I'll talk about something entirely different, and that is using broadband techniques to try to understand chemical kinetics and reactions, but we probably won't have time for that. So the goal here for us is to get in situ calibration-free methods for measuring these isotopes of carbon in this case. These are going to be tabletop, accurate, and hopefully SI traceable instruments. That means we can assign an uncertainty to the measurement without actually calibrating. Okay? And of course, while pushing on the accuracy, we also don't want to lose one of the more important things of relative methods like mass spectrometry, and that is their incredibly high precision and it's good stability from that perspective. So in a lot of these applications of which you're well aware, we need to be able to make a precision measurement at least at the 1/10%, or the sort of 1 per mil level. And in most cases, to learn any really useful science, you have to be at a 1/10 of a per mil or even lower than that. So there's a really high bar set by the existing methods, and that's going to be a real challenge for our precision in addition to trying to make accurate measurements. So what we're doing is nothing totally new, right? So we're doing optical spectroscopy, and we're looking for isotopic shifts in molecular absorption features. So this is sort of exactly what the citation was for the Nobel Prize in Chemistry awarded to Harold Urey. So since different isotopes and different molecules then have different energies for vibrations and rotations, their absorption features are shifted around in the spectrum. And what you see here in this sort of secondary line, I'll use the pointer as well, in this line here, so this is a measurement of deuterium. This is a deuterium shift from a major hydrogen peak in the middle. And this was the first observation and isolation of deuterium in this case. So this is something that's notoriously difficult to identify in mass spectrometry because it's always there from a little bit of water that seeped into the system. So this was an optical measurement. So we're doing the same thing, leveraging these optical shifts to get at different isotopes. Our technique is something that's probably relatively familiar, and that's cavity ring-down spectroscopy. So we're operating in a linear absorption regime. We begin, in most cases, with a single frequency laser, as you'll see on the left here. This is a continuous wave laser operating at one frequency, and we'll have a fast optical switch, which is represented here as a acousto-optic modulator. That fast switch will send some light through some mode-matching optics and into our optical cavity, and then that light will be focused onto our photoreceiver for processing. What you see in the picture on the right is one of the decay events. So once we turn off the switch, you'll see the light begin to decay, and by measuring that ring down time, or the decay time constant, we'll get a measure of the losses inside of the optical cavity. Here's just another image of a similar technique, and what I'll point out are these sort of two mirrors that we've got pictured here in the middle. So sort of these two optical components here. Those are the optical components that create the optical cavity. So our gas sample will be housed in there, and the reflectivity of those mirrors in our laboratory instruments is usually 0.999 or higher. So we're getting tens or hundreds of ppm of light of intensity transmitted through the optic. But once that light gets into the cavity, it's going to make many thousands of passes back and forth. And what that's going to do is increase our effective path length. So on the previous slide, I quoted a number that's about 10 kilometers of effective path length. And this is on about a meter length tabletop piece of equipment. So that's where we really generate our sensitivity from. The photons that we're measuring have really sampled the molecules many thousands of times, and therefore we can achieve high sensitivity by measuring that purely exponential decay and measuring the loss time constant as a function of frequency. So that's what we show here. This really is just a pure exponential decay from this resonator. So we measure tau. We step our laser, measure tau as a function of frequency. And here you see in slide number 2 here on the top right, there's an absorption feature from CO2. So what's plotted is 1 over the speed of light times this time constant. All right, so this is an absorption coefficient on the y-axis. That absorption coefficient alpha is related to the time constant with and without absorption. That's it. If you work better in transmission space, the absorption coefficient times the effective path length, exponential of negative of that quantity, gives you the transmission spectrum. So this is the equations don't get any more complicated than this one here. So 3 is the most important to us in the laboratory. So again, we're measuring alpha, this absorption coefficient. We know the line shape function usually pretty well. You can start with a Voigt. There are more complicated line shapes there, but there's different broadening mechanisms. We have a pretty good handle on what those are. NS here is the total number density, and chi is usually a mole fraction of the absorber. So for example, if you're looking at CO2 and air, chi would be about 400 ppm, and NS would be the total number density proportional to pressure and inversely proportional to temperature. The unique thing that we'll talk about a little bit more in detail here than you probably usually think about is S. So this is the line intensity in this nomenclature, or related to the absorption cross-section, or so the probability of the transition. These are the things that usually aren't known accurately. They're populated in databases like HYTRAN, but the idea here is if you want to measure alpha and know the mole fraction accurately, you've got to know the transition cross-section accurately, right? And those parameters are sort of notoriously difficult to get at. I'll show you how we get at them accurately at NIST, and then sort of flip things on their head and try to leverage them to get at number densities. So I've already described how we go about measuring the absorption coefficient. Our x-axis is frequency. We know how to measure frequency really, really well, mostly thanks to a lot of work here at NIST and Boulder and other places. The ring down time, that's a measurement of time. We know how to do that really well with high traceability. If we can put a sample inside of our cavity with a known mole fraction, then we can know chi with traceability to the mole and to the kilogram. So these are SI units. And we do that in our group in Gaithersburg. The gas sensing metrology group supplies reference materials in the form of gas cylinders. And they've done intercomparisons with NOAA and different places like that. So that's something we can do really well through gravimetric methods or through volumetric methods. Again, the line shape function, excuse me, the line shape function and the total number density are proportional to temperature and pressure. So those things we know really well. So if we have a sample where we trust the mole fraction, then we can make an accurate measure of the line intensity. Why is this really important? Well, here's an example of average global CO2 as measured by the OCO2 satellite mission from NASA. So you can see all of the variations in this image between blue and red. The total span there is about 15 ppm of CO2. And that's on a background of course, about 400. So we're talking about the total range of amounts that you need to measure on the order of about 15% of the base value. So if you want to retrieve those concentrations to much better accuracy than that 15%, then you need to know the line intensities. This is an optical instrument that looks at reflected infrared light and looks at absorption from space. So the better that we can know these spectroscopic parameters, the sort of better the resolution in these sorts of maps can be. This is one of the more challenging measurement problems, is CO2. You've got to have spectroscopic parameters known to better than 1% to start to think about tracing out ppm levels of CO2. So we've shown that really recently, that for the strong major isotopologue, we can get instrument intercomparability. at this sort of 0.1% level. This is something new that I don't have time to talk about specifically, but we're starting to reach this level of measurement for S, for this transition intensity, that hits this sort of 0.1% level. So sort of back to what we hope to do for things other than the major isotopes. So can we redefine, can we even think, these are really sort of grand challenge questions, right? We're not going to be able to do all of these things now or maybe even in the foreseeable future, but these are sort of grand challenges that we like to think about. Is it possible to redefine an isotope measurement system to true invariants of nature instead of a marine fossil sample or something like that? Can we measure direct isotope amount ratios to better than a per mil or so? And by pursuing that accuracy, can we make sure that we don't sacrifice on precision? That's really difficult. And hopefully the outcomes of these will be, can we improve scalability? Can we go beyond standard isobaric interferences, remove oxygen problems, things like that? Okay. So the first test system is radiocarbon. So it has a half-life of 5,730 years. And the natural abundance in the atmosphere is approximately 1.2 ppt. So that's the highest amount of C14 in a neat sample of CO2 that we would ever try to look for. It's 1.2 parts per trillion. So already that's a pretty daunting measurement challenge, because we'd like to be able to go well below there. We'll define a fraction modern of C14 as just that, the sample amount over this 1.2 ppt. And you'll see at a couple times throughout the presentation, there'll be this big delta. It's pretty analogous to the delta C13 scale, where we're just measuring the sample relative to a reference. Now this sort of natural, stable 1.2 ppt atmospheric amount of radiocarbon has been subject to some major perturbations in the last 60, 70 years or so. And this is the bomb curve for C14. So you'll see here, this is a delta scale on the y-axis. So through the open-air testing of thermonuclear weapons, the amount of C14 in the atmosphere almost doubled. So 1,000 in big delta there would be twice the amount. And then since about 1970 or so, both in the northern and southern hemisphere, that total amount of C14 has started to decay, mostly through exchange with the oceans and mixing in the atmosphere. However, it's not the only reason it started to decay. So on the right, you see projections from a number of continued trajectories for global burning of fossil fuels, where the sort of flat bar here is if we just decide today to stop. What you see is that the continued introduction of old carbon into the atmosphere has the effect of driving down the amount of C14 in the atmosphere. So all of the burning of fossil fuels from coal and natural gas are entirely depleted in C14. So that was me down in Wellington and at Bering Head, which is one of the sort of collection sites. So this bottom curve here is the southern hemisphere curve. And that's a real pristine spot where you get really beautiful, clean air coming in from the Southern Ocean in that case. But, this bomb effect has also been monitored in great detail not too far away up at Niwot Ridge. And this sort of trend, people relate to the amount of fossil fuels being released into the atmosphere. So one more sort of example of why precision measurement of C14 is maybe a really important measurement problem to tackle. This is from a 2010, so already a fairly dated National Academies report, but the gist of that report was you'd like to be able to create these grids where you could get sort of 10 to 15% uncertainty in the amount of fossil fuel emissions in the U.S. This is from a top-down perspective, a measurement perspective. So in order to get those grids, one of the things the National Academies recommended was, well, why don't we build one brand new AMS facility and dedicate it 24/7, 365 to trying to make this grid. So that's a one-time $5 to $10 million investment in the facility, and then staffing the facility and running it around the clock, running samples, and all that gets you is this grid. So where I'm at now in Washington, D.C. is right here, and then there's Baltimore and Philadelphia and New York and Boston. They're all sort of right at the intersection of one of these grids, right? So clearly there's going to be some challenges in trying to get national and state level cooperation and understanding as to what these emissions sort of look like. So what we've decided to do, what our approach has been, can we build a tabletop instrument that might be more cost effective but still have the sensitivity to measure C14 at ambient levels so that we can contribute to this sort of debate. The way we have to do that is build one of these optical cavities, and we have to get the optical cavity cold. So the reason we have to do that, because of the really low amount of C14 in the sample, basically everything else absorbs first. So all of the clumped isotopes absorb first, really hot bands of the major isotope absorb first, high J transitions absorb first. So the first thing we have to do is cool this sample down and try to collapse the sort of Boltzmann factors for all those lines we don't care about. So if they're transitions that start in elevated rotational and vibrational levels, we need to quench them out of the system. So we need to operate at around 200 Kelvin. And this is what our first generation instrument looked like on the table. So we're looking back from the second mirror, sort of down the cavity. And if I go back one slide, this is a cold finger that runs along the inside of the cell. So this system here is the cold finger. So our gas sample sits inside the cold finger, and the cooling liquid does bulk cooling. We have a ring down mirror here and a window on the back side. So that's what you see in this next picture. Again, looking back through the second mirror. What's important from our perspective in the laboratory is that the length stability is reasonably high. So the length of this cavity, which is 1.5 meters in this case, is stable to about a part in 10 to the 8 over an hour's time. What that means is the frequency of our mode that we're interrogating doesn't move all that much, less than a megahertz drift. The volume of this cavity holds about 3 liters of gas. So what that means is we need about 18 milligrams of carbon to do one measurement. That's quite high. The AMS community can often deal with micrograms of sample. So this is going to be a very different measurement case, potentially suitable for atmospheric applications where maybe we've got a little more sample to work with than maybe your most demanding archaeological applications where you're trying to radiocarbon date a rare material. That's going to be more difficult for these larger volumes. But again, we're on a tabletop instrument, so there's other advantages there. So I've finally gotten to a spectrum, real one anyway. So this is us. This is our first measurement of the radiocarbon in biogenic CO2 and petrogenic CO2. So petrogenic being CO2 derived from the burning of fossil fuels, and on the left was CO2 captured from a corn ethanol burning power plant. So on the left, you see the difference between these two is just this little bump on the left. So this little bump on the shoulder here that's marked C14, that's our absorption feature that we're looking for. And it's not here in the petrogenic case. The strong line that you see to the right is a transition that we're attempting to cool. So our target was to get down to 200 Kelvin, and if we had gotten down to that level, this C13 transition would be about commensurate in size with the C14. We only got down to about 215 or 220 Kelvin in our first system. So there's still a relatively large interference there. But we do have direct access to some C13 information in the same sample, which might be interesting. Yeah, so as I mentioned, that C13 line is actually 2. There's 2 overlapping transitions in here, which makes life a little more complicated. But we can handle it with a really good model. There is an N2O line that's really frustratingly right here. So if you're dealing with atmospheric samples, you've got to clean the N2O out of your sample to down to a part per billion. That's challenging. It's not straightforward, but there are techniques to try to do that. Thankfully, in this first sample, we didn't see any N2O in the biogenic. It's in the petrogenic, actually, just a little bit, at about 15 ppb. So this is the same scale on the y-axis. So we're a little taller over here. A little bit taller on the right is just from that little bit of N2O interference. Thankfully, we can tune our laser a little bit to the left. So this is the same relative frequency scale. So 0 is the C14 transition. So now we're about a gigahertz to the left to lower frequencies. So this really nicely isolated N2O transition that we can use the same instrument to measure. In this case, I think it was about 15 or 20 ppb of N2O. We can do that at elevated temperature. We don't need to go terribly low. And we can do C13 analysis through FTIR or other methods to really try to back out what the fraction modern is. So the number we sort of measured was about 0.75 fraction modern for our biogenic sample with about an 11% uncertainty. So again, full uncertainty here. That matched pretty well with the AMS value, which was about 0.8. So we were relatively happy with that. We have some work to do on the null case because our fit is sort of pushing into sort of negative C14 area. And we think mostly what's happening there is just we've let our fit go sort of completely loose. And it's trying to push this C14 line down. And I think that just means the wing of the C13 line. The model isn't known quite as well as we need it to be. So we're going to have to do some more survey work in this region to get the interference modeling down or go to colder temperatures. But it's reasonably close to 0. And of course, we could just tell our fit that it's non-physical to go below 0. But we were really trying to get a grasp of how flexible our model was. And it's a bit flexible, but we think still within reason we can strongly differentiate between the two. What you're seeing on the left are cumulative probability distribution plots for repeated measurements over many months on these samples. We can really clearly distinguish between the two. So I don't have to go through the big scary chart, but the outlook for this is 11% fraction modern isn't going to set any world records for sensitivity, but it's already on the cusp of potentially being useful in certain areas. So one of them being the sort of direct investigation of biofuel blends, where you really just need to know, am I at 15% corn ethanol or 10%, or am I at 40%? It's just almost like a binary measurement. Is it yes or no in those cases? So that was our first generation instrument. And right now we've got a Gen 2 instrument on the table, and our target sensitivity there, based on all of our modeling, is that we're going to be able to hit this 1% level, and that sort of pushes the application space a little further. So I don't have any new data, but we're finalizing our low temperature testing and our optical alignment. It's a bit more complicated, but it's really just a much better vacuum jacket. That was a major source of our heat loss. So again, this is an 8-foot outer tube here. So this is 8 feet long. And we do have a closed loop cooling bath here. But at least still fits on an optical table. So I can still claim it's sort of a tabletop instrument. And we have interest in pushing beyond this Gen 2 for C14. So yeah, so that's our C14 story. So if I could talk a little bit about C13, C12, this is a really new space for us. But the idea is to make absolute isotope ratio amount measurements. And again, sort of Harold Urey pops back into our broad introduction here. So if you're familiar with measuring C13, C12, that's usually done on the Vienna PdB scale. The Vienna PdB scale is traceable to this original PD belemnite sample, which Heinz Lohenstamm, working with Harold Urey at the University of Chicago, actually picked up originally on a field trip to this PD region in South Carolina. They came back with this marine fossil, and they got to the lab, they mixed it all up, and they made repeated measurements on it, and it was super uniform. They were really disappointed, according to what I read anyway. Right? They were disappointed because they were hoping to measure all sorts of different C13, C12 ratios in this different sample that they brought back, and it was incredibly uniform. So that made for a great reference material. So that's sort of the origin story of PDB as a reference material. It was sort of this accidentally uniform sample. But of course, with a sample like that, you can't distribute it forever. So there was a process to establish the Vienna PDB scale so that new reference materials could be made, which were traceable to PDB, and we could sort of get a chain going here. So we've gone from the original sample, MBS 19 was what you used to realize Vienna PDB. Now IAEA has a sample 603, which has replaced MBS 19. So these things get discontinued and a chain starts. So the idea is, can we link these sorts of scales, again, to these true invariants of nature through these transition intensities? And there's a whole host of applications, which I'm sure many of you are well aware of, where you can differentiate between different samples on this Vienna PdB scale. So the idea here is we're going to put a sample of CO2 and air into one of our optical cavities from a cylinder where we already know of delta assigned on the Vienna PdB scale. So we're going to have our cylinders be of CO2 where there's already a Vienna PdB assignment. Then we're going to make direct measurements of the isotope ratio amount in that sample. So the equation for getting yourself on the delta scale, again, just for reference, is down here. So we know delta 13C from IRMS measurements, isotope ratio mass spectrometry measurements on our cylinders. We can do that in-house at NIST. We're going to measure directly 13R. So that's what we'll get from our optical spectroscopy. So we do that in this case with a 2-laser system with a third laser, sort of a 3-laser system. 2 of them are probing molecular transitions of interest. The third one is just there to stabilize our cavity length. That's what the INI's there for. But we have a transition in the telecom regime at 1572 nanometers that we'll use to study carbon-12, the 626 isotopologue. And then at 2 microns, we're going to interrogate the 636, the carbon-13 isotopologue. The reason we use 2 transitions is now with two lasers is we can pick 2 transitions with relatively the same level of absorption. So the dynamic scale of our instruments doesn't need to change when I look at C13 and C12. We can also pick transitions that have the same ground state energy, so the same ground state rotational numbers. And that means that if I measure them simultaneously in the sample, the C13, C12 ratio is invariant temperature changes inside the sample. So oftentimes you'll see in the literature people will pick one laser and they'll do cavity ring down spectroscopy, or maybe you have experience with a commercial instrument that'll do cavity ring down spectroscopy or direct absorption spectroscopy with one laser. And usually you can find a region in the telecom where you can see both C13 and C12, but they're going to be vastly different ground state energy levels, vastly different absorbances. So dynamic range and temperature drifts can be a real challenge for those instruments. So that's why we've chosen this sort of design. So these are the cavity ring down spectra. Again, these are, let's see, 5,000. Yeah, so these are a pair of C13 transitions. Occasionally there's a little bit of water in their wings that we have to know where it is and care about, but we can handle that through good modeling. And then we have a couple of transitions out to the blue that we can use for the 626. So what I've plotted here, maybe a bit difficult to see, but there are dots here, 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 and here. So the 5 dots are our measurements of R13 sample from the optical instrument versus the Vienna PdB delta values assigned by our IRMS. You can see that the linearity is excellent. And if we fit this line, all we're left with is fitting the slope. And the slope is the carbon-13, carbon-12 ratio of the reference. That's how the delta scale is defined. So as long as we trust the delta values that we've assigned, we're getting a peak, a first estimate into what's the true C13, C12 ratio in the reference material. So other folks have tried to do this with mass spectrometry and tried to link to gravimetric standards. So we'd like to see how we compare to those measurements. We repeated these measurements on 5 samples, all sorts of orders and varieties for about 6 months' time. It's a pretty normal distribution. The sort of mean value we get from this distribution is our dot way here at the end. These are a whole host of relatively recent measurements through making mass spectrometry measurements on sort of gravimetrically prepared samples, trying to get at what the true 13R for Vienna PdB is. And these are sort of, for historical purposes, some often quoted values. So if you go to Wikipedia and look up the delta 13 Vienna PdB scale, this is the Craig value. that is most often quoted. This is a value measured in 1990 that was chosen by IUPAC to sort of be the new IUPAC accepted value. So anyway, recent measurements show that things are maybe a little bit different than we thought. But what's exciting for us is that our error bars for accuracy in this measurement are at least sort of on the scale of the IRMS error bars for accuracy. And we're at about the 10th of a per mil precision in about several minutes of measurement. So we were hoping that there's room to also improve our sensitivity. But at least from an accuracy perspective, our error bars are doing, we think, quite well for this sort of first proof of principle idea. Can we get an optical value for this reference point? Of course, what we like to do is get samples of the primary reference materials and all the secondary reference materials and throw them directly into our spectrometer, and we think that's where we're headed. Okay, so I've been going for a little bit already. So I think I'll see how am I doing on time? Okay, well, I won't take all of that. maybe 5 minutes. I can give you the speed version just because it's one of my more favorite topics to talk about. So this is we're going to move away from CO2 specifically, move away from isotopes, and we're going to talk about new technique development. This is something that I started here as a postdoc at GILA, and it's something we're just getting into in our laboratory in Gaithersburg. So the idea is to do time-resolved frequency-comb spectroscopy. So why would you want to do that? Well, there's a number of advantages of frequency combs, and it's important to remember that just because you say the word frequency comb doesn't mean you're going to get all of those advantages. All right, so you need to think about what advantages you really want for this laser to leverage. So for us, we want all the high spatial coherence, high temporal coherence. We want to couple this laser to enhancement cavities again, so we can get over broad spectral bandwidths now instead of just a CW laser. We can get cavity enhancement. High spectral brightness, so we can do things like dispersive spectrometers to get high time resolution. And of course, absolute frequency accuracy, again, this whole sort of NIST approach to getting really high precision reference data. So originally we were looking to study free radicals, transient intermediates, and more recently in Junyi's group, they've continued to push on this with Bryce Bjork and Tin Bowie, who are a fantastic graduate student and postdoc who are also working on this project. And they really pushed things the last few years to measure sort of the entire chemical kinetics reaction pathway for the reaction of CO plus OH, and they're looking at CO2 formation here. So there's a whole host of additional experiments which I'll just sort of breeze through. But the idea here, how do we get high time resolution so we can, over a broad optical bandwidth, sort of do the things that StepScan FTIR can do? How can we try to monitor reactants, intermediates, and products simultaneously? So we need at least sort of microsecond or tens of microsecond time resolution. So the way we get that here is we build a two-dimensional dispersive spectrometer. So we take our optical frequency comb, send it into our sample, and then this is work done by Scott Diddams here at NIST originally. So we'll send our comb into a tilted etalon. This is termed a virtually imaged phased array. It's a neat optical tool that basically gives you higher dispersion than a ruled diffraction grating. That's what's most important about it. So we get high dispersion so we can really disperse light in the vertical direction, and then we cross-disperse with a grating, and we get this two-dimensional map on our camera. So limited by camera integration times, which can be microseconds or so, we can get a full two-dimensional map where we can map frequency to pixels on the camera and then back out a one-dimensional spectrum. So that's the idea. In Gaithersburg, we have a commercial frequency comb system, and we've just started looking at single-pass transmission through samples, things like high concentrations of N2O and CO that we can do quite readily. Our frequency comb system gets coupled into a mid-infrared fiber. So this system operates from about 4.4 to 4.7 microns, so right around 2200 wave numbers. And the transmission through sample will get coupled to a single mode fiber and then into our dispersive spectrometer here. So this is what camera images look like when you have absorption in the way. So this is the rotation resolved absorption from the strong band of N2O, right around 2200 wave numbers again. So the dots are where light didn't make it through our single pass cell. This is what the camera image looks like when there is no absorption. So this is sort of our reference image. So if we can take these two images, we have a direct measure of I over I naught at camera integration times. That's our transmission spectrum. We have to calibrate these images. We use CW lasers and etalons and all sorts of fun things, but I'll sort of skip through that. But this is what the spectrum of N2O looks like in that region. Again, this is a relatively high concentration of N2O, 0.6%, but it's just a short single pass system. We haven't coupled to a cavity yet. So this is at, we have absorbance noise that's approaching 10 to the minus 5 at a second of integration. So that's pretty good absorbance noise. So for sort of a comparison, the best numbers that I've heard of from like Aerodyne multipass cell, like those measurements for making isotope ratios or something like that, those hit absorbance noises about 10 to the minus 6. And that's really sort of the state of the art as far as I know, even for sort of laboratory equipment and commercial instrumentation. So for a first pass, we're doing reasonably well on noise. We can compare integration times. So a 50 microsecond integration time is just the blue dots. And then if I average out to a millisecond, we start to get these red traces. So we're getting pretty good averaging, and we're in the process right now of doing a full sort of Allen variance analysis and figuring out how well we're doing. You know, importantly, we want to look at time evolution of these signals. So this is just at the camera frame rate this time, which is about 100 hertz. We're getting, what was the integration time here? Probably 10 microsecond snapshots at 100 hertz rate, and I've just simply opened up the valve to the pump in this case. We can start to see all these absorption features wash away. And that's what we did. That's essentially what we did in the original measurement. We were looking at a photolysis measurement where we put a precursor into a cell and we smashed it with a 193 nanometer photon. Precursor blew apart. We saw all these intermediates, the HOCO intermediate, and these things sort of evolve and fall away. So we think this is going to continue to be a really powerful tool for studying both rotationally resolved species with reasonable time resolution, broadband absorbers. There's an SF6 band here. So this was a really rough spectrum. Again, on the top is PN and L, and on the bottom is our really rough 1 second spectrum. All these little sort of spurs and dips that you see here are just a consequence of not doing the best job normalizing this first image, but it's just something that was taken pretty quickly. But the idea is there. We can look at broadband absorbers, narrowband absorbers. So that means a broadband precursor, getting photo-bleached, lines coming in, secondary chemical reactions occurring, radical reactions occurring, and then looking at long-term products. So this is where we're going with these sort of broadband fast tools, and something we're building up a little more in Gaithersburg. So I'll stop there just with the really broad overview of that story. And I'll mention some people who were, I specifically had as co-authors, especially because we don't have all this stuff written up yet, but Dave Long in the middle, and Joe Hodges, and Zach Reed are all also research staff and excellent colleagues at NIST, so I want to acknowledge them. Erin Atkins is also research staff with us at NIST, and although you didn't see her name much today, she's working a lot on oxygen measurements, A-band, single delta band, so those are, again, things that we're working with the CO2 community on. And Melanie Geisels and Hongming Yi, both guest researchers. Hongming's moving on shortly, but he did a good bit of work on the C13-C12 ratio. So that's an older picture of the lab, but I want to acknowledge all those folks. And thanks so much for your time. It's a pleasure to be here, and I enjoyed the visit. So thank you.
We have time for questions. I'd like to just start out with a comment. It seems like the stability requirement for your cavity is going to keep this thing in the laboratory for the foreseeable future. What do you think about that?
Yeah, it will probably be up to more clever people than I to maintain that level of stability. For the C14 instrument, that level of stability is maintained just by operating in a temperature-stabilized room. So, of course, that's something that is more difficult to see as you get more adventurous in the field. But we're talking about 30 millikelvin stability over an hour in that room to get to that level of stability. We do actively control the length of these cavities if necessary. So I had mentioned the Heaney laser for the C13 work. So in that case, our optics are coded both high reflectivity for our probe wavelength and modest reflectivity for Heaney. So we actually have a Heaney mode so we can stabilize that cavity length to the ini. So there are active ways to do it. Then it just becomes a question of bandwidth in your actuators, and can you hold things stable in the conditions that are challenging. But yeah.
Questions for Adam? Way in the back.
Yeah, thanks very much for your presentation. I feel like I might be missing something really key. Help me understand, like when you compare your system for isotopic measurements to existing commercial systems, those are also based on CRDS. Some of them do have multiple lasers. So where's sort of the new piece coming in that allows you to advance your accuracy and stability?
Yeah, no, that's the exact key thing that I have to try to differentiate, because oftentimes the multiple laser commercial systems will just be to give you more species. So I'm not aware of a system that's using multiple lasers to get at the different isotopes in exactly the same way that we are for the C13. And again, that's a matter of sort of cost in a lot of cases. So to get the high reflectivity optical coatings for the mirrors to match those exact wavelengths is maybe a little more challenging than additional wavelength pairs. So one balance is sort of cost and complexity of the mirror coatings. And to the question of really broadly speaking, what are we trying to accomplish that the commercial instruments aren't? From my understanding, the commercial instruments require really frequent calibration to calibration gases. So our goal, and again, in a very controlled environment in the laboratory, but our goal is to see if we can make accurate and direct measurements using the direct absorption spectroscopy sort of as promised, without having to use the calibration gases to ensure our system is operating in the proper regime. So if we have good faith in the transition intensities, then we should be able to trust the spectroscopy on face value, as long as we also understand our sample conditions well enough, like temperature and pressure. So the idea is to get accuracy without gas calibration. Yeah.
Yeah, just maybe two quick questions. So commenting on the last, does that mean that the commercial units are using a modulated technique? Is that why they need the calibration? They're not doing a direct absorption?
Depends on the commercial instrument.
Okay.
Some of them will do modulation techniques. Some will do direct absorption only in an on-off configuration. So they'll have a laser parked just at the top of an absorption feature, and then they'll occasionally check for baseline. So we make sure to measure out the entire absorption spectrum. And what that gives us is the opportunity to look for really sort of nasty things that might pop up, like water is always the problem, right? So if you're just checking the peak and you start to get a shoulder on your absorption feature, the peak isn't exactly the peak of a symmetric line shape function anymore. So the modulation spectroscopy absolutely needs the calibration. And I think oftentimes these on-off measurements are susceptible to drift in the long term in terms of the frequency axis, although of course those companies work quite hard to mitigate those challenges. But I'm not a user of the commercial instruments. We have a few in the gas sensing group that folks use in a very controlled environment. But from what I understand talking with folks is that there's a lot of gas calibration that needs to sort of continuously go on to make those fit in.
And in just 1 second follow-up is, I'm just curious on why you are, or maybe you could just help me understand why you guys landed on just a linear cavity for your choice of doing cavity ring down.
Sure. Well, linear cavity in this case, the geometry based on the radius of curvature of the mirrors and the length of the cavity, we've chosen a geometry which fairly well isolates higher order modes, so higher order transverse modes in the cavity, so things that would sort of interfere with this nice purely exponential decay. So that's one choice. The other choice, and this is something that I don't think was a prime concern originally, but it became a concern, especially in the mid-infrared, is the mirror coatings in the mid-infrared still maintain a fair bit of birefringence as compared to some of the coatings that are used in the telecom regime. So working with the 3-mirror cavity system, you actually have strong loss dependence to the linear polarization of light that you couple into like a 3-mirror cavity, because you're making non-normal incidences with the dielectric medium, with the coating. So with the linear cavity, we've tried to avoid just little drifts in polarization leading to little drifts in our time constant, which would be a problem for our sort of baseline. So the linear cavity, we thought, eliminated that. Didn't quite eliminate it because the coatings are still relatively birefringent out in the mid-infrareds because it's a sort of a new technology. But we've been able to handle that. And we've studied that in detail.
A question from Mount Stupid. Can you do Doppler-free saturation spectroscopy with cavity ring down? Is that
Absolutely.
Is it actually a viable option for something like carbon isotope detection?
Absolutely, and it was actually so we're not alone in building optical instruments for measuring radiocarbon. We were sort of the first ones to get together linear absorption spectrometer to get to these fraction moderns and below. But beginning already in 2011 and again in a paper in 2016, a group at INO in Italy has been using saturated absorption to measure radiocarbon. So the acronym is SCAR, but it's essentially it's a saturated absorption ring down measurement. So what they're doing is they're pumping so many photons into the cavity that you get nonlinear absorption right at the line center. So just as you said, it's a subdoppler feature. And at the first bit of your decay, your sample actually looks transparent. So at that first bit of the decay, you're actually getting a direct measure of the base losses of your cavity. So it's like a baseline measurement. And then the amount of photons in your cavity drops below back into the linear regime, and then you go back in exponential. So the idea is you get base losses and absorption losses in one ring down event. At the end of the day, those two numbers are really correlated. So you need to do a lot of work across the line to decouple them. And it's pages and pages of algebra and derivations to get out the parameters you really want. Where in the linear absorption case, it's really just that one alpha equation. So it's one simple line, and you don't have to worry about nonlinear phenomena. So the answer is yes, you can absolutely leverage those nonlinear features to improve sensitivity. But to maintain accuracy, it gets really hairy really quickly. Another reason is those interfering transitions nearby. So sort of the tail of that it'll take me a while to get back there, but you get it. The tail of that C13 line and having N2O in that sample, when you get to lower C14 levels, about to be commensurate with maybe like a 10 ppb of N2O in there, now you actually are saturating the N2O transition as well on the fringe. So now you've got to model the nonlinear saturation of the N2O transition and the nonlinear saturation of the C14 and the nonlinear tail of the C13, whereas for us, those three things sum linearly. So it makes the modeling simpler.
So it actually doesn't help you separate interfering species. It makes it worse.
If the goal is sensitivity and number density, yes, it makes it worse. Where people have really leveraged the subdoppler features is to get at the actual transition frequencies. There, of course, is extremely powerful in identifying the individual transitions that occur in overlapping Doppler broadened spectra. So there's a lot of work in that community for populating high tran and things like that, but just on the frequency side, so on the x-axis side, whereas here we're really trying to push on the y-axis.
I have a question, and it may not even be related to exactly what you talked about, but you started out with traceability scales, and for CO2, there we still rely on the NOAA standards, the gas standards, and I know NIST is working on a CO2 standard. How far along is that work?
So I know there are two. There's at least one standard where there's been a really robust intercomparison between NIST and NOAA and their ability to analyze and gravimetrically prepare, but mostly in that case sort of analyze and assign values for CO2. So that was the Northern Hemisphere air, so a set of cylinders that were taken from Niwot Ridge and distributed. So NOAA and NIST were in full agreement in terms of each respective uncertainty budget for assigning CO2 mole fraction in a gas sample. So there's also a Southern Hemisphere air reference material, which is from the Bering Head site in New Zealand that NIST supplies. So it's also met the same sort of rigorous value assignments that were done in comparison with NOAA. But I think the interaction between those two groups is there's plenty of room to grow. Yeah.
If I could, I have one more isotope question for you. There was one point at which you were talking about, it was I think during your C13 section, where you were interested in trying to back out the ratio of C13, C12, and the standard, the V PDB standard that you were looking at. And you made this comment about you can do this so long as you have confidence in the delta values you're putting in. So maybe it's because of the way I'm used to dealing with these reference standards like SMO and PDB. I feel like the deltas are based on our confidence in those standards. So how do we flip that on its head and say if we have confidence in the delta values, then we can actually back out the standard?
I understand where you're coming from. So I'm still learning how best to speak this language. And I'll probably learn a lot at AGU in a month when I get a lot of questions there too. But so from my perspective, doing the optical spectroscopy where I'm talking about percent or tenth of a percent levels, we're pushing as hard as we can to get to like a per mil uncertainty. From that perspective, the uncertainty in assigning a delta value using IRMS is actually negligible. So if I take secondary reference materials from NIST, or if I take the IAEA primary sample, or if I still have MBS around, whichever of those reference materials I use to establish my IRMS scale, the uncertainty associated with that choice, according to the literature and according to my reading of this, is below a tenth of a per mil, right? So yes, we are using secondary reference materials to get those delta values, and it would probably be preferable to somewhere in that loop have a primary reference material, whether it's introduced in our optical instrument or used as the reference for the IRMS. But from my perspective, the uncertainty associated with any of those decisions, the uncertainty in the delta assignment is not significant compared to the optical uncertainties, if that makes sense, because it's a relative measurement. It's a ratio of ratios. So it's a small contributor here. Yeah. But that raises the next question, right, which is, okay, if the delta value is assigned with such a low uncertainty, then what contribution are you making by having, a 1 per mil accuracy or something like that? And the answer is just simply the difference between making the precision delta assignment and determining the accurate actual ratio. And the accurate actual ratio, the RMS community is still sort of stuck at this per mil level for the accuracy for the C13, C12. So yeah. Hope that helped a little bit.
Other questions? Well, let's thank Adam. Thank you, Adam.